So, good afternoon, everyone. Uh, Thank you very much for being here in the third talk in Computing and AI Talk series. We are very fortunate enough to have Dr. Alpan Raval as the third speaker. As you know, the purpose of the talk, Computing AI Talks, that we started 2 months back, is to have a glimpse of the wider application that AI has in different areas. And we have been very fortunate enough to have very good speakers who have touched different aspects. So we had Pushpak Bhattacharya who talked about NLP. Then we had Ricardo Vinusa who talked about how do we do in fluid dynamics and so on. And now we have a very interesting talk coming up by Dr. Alpan Raval, who would be talking about AI for social impact. And basically, he would be talking about the work that his team, he leads a very good team at Wadhwani AI, and he would be talking about the work that Wadhwani AI does in different social sectors, different problems that are of direct relevance and specific importance to the society. So as a customary and as my duty, let me please introduce Dr. Alpan Raval. So Dr. Alpan Raval is, well, many people already know you, but just as part of my duty, I would be introducing for those who are from other disciplines. So Dr. Alpan Raval is Chief Scientist, AI and ML at Wadhwani Institute for Artificial Intelligence. He is theoretical physicist by training with a PhD from University of Maryland and undergraduate degree from IIT Kanpur. He has diverse background spanning black hole physics and cosmology, computational biology, applied mathematics, and machine learning. And prior to joining Wadhwani AI, he also headed an applied AI team responsible for deploying machine learning models for feed content at LinkedIn. We all know what LinkedIn is. Earlier on, before that, he taught mathematics and computational biology as tenured faculty member at Claremont College in Southern California, and worked as researcher in DE Shaw Research. He has also written a book on genomics-based network biology, titled Introduction to Biology Networks from CRC Press. So we are very fortunate enough to have you, Dr. Alpan Rao. And without taking much time, I just pass it on to you. So we have about 1 hour for the talk, and I think we have your permission to record it.
Sure.
Yeah. So, and we are doing it live stream on YouTube. And so at the end of the talk, just a little housekeeping rule for everyone. So we have kept everyone on mute. And once the talk finishes, you can raise your hand if you have a question, and we'll unmute you. You can have the question directly, or you can also type in chat box. And those who are on YouTube, you can write in the chat box in YouTube as a message, and we'll pick up the question and we'll route it to the speaker. So thank you, everyone. And I present to you a very exciting talk. And thank you, Dr. Rao. Stage is yours.
Thank you, Vivek, for inviting me to talk in this series. I know I'm following very distinguished speakers. And also thank you for that kind introduction. And with that, let me first spend a few seconds sharing my screen. This will just take a few seconds. Yes. So I'm going to talk today about the work we do at Wadhwani AI. Our work is all geared towards social impact, and we are an independent nonprofit institute. Our charter is to build AI-based solutions that directly impact underserved communities across the developing world. So that's our very specific charter. We only work on problems that have a strong AI component. We only work on problems that will impact the underserved and across the developing world. The way we work is dictated to a large extent by the domains in which we work. There are some common elements, no matter which area we work in, and the common elements is really how things are structured. So you need more of a systems approach in order to make AI solutions feasible or have them make a difference in the social sector. What I mean by systems approach is really two things. On the one hand, one needs to be aware that the AI is really a small piece of the global solution. So the AI typically sits within a larger product. The product is part of a solution to a social problem. The specific solution to the social problem is part of an entire program of interventions and so on um, that needs to be in place in order to effect long-term change. So the AI sits, as a small piece inside this, and in order for this whole thing to work, it's very necessary that we work in teams that are inherently interdisciplinary. So our teams, typically when we attack a problem, our teams are composed of technology experts. That's people who have qualifications and experience in AI and machine learning, engineering teams, user design teams, program teams, and so on. We need people with domain expertise depending on the domains in which we work, and these are people who have expertise in medicine and agriculture, again depending on the problem space. And in fact, we have medical doctors and agricultural experts as part of our team here at Wadhwani AI. We need implementation experts. We need frontline staff who will help in collecting data, who will help in making sure that the solution is deployed in the right way. And finally, we need, for much of our work, in fact, for almost all of our work, we need to work closely with either central or the state governments. Now, there are various challenges in this whole process. And when you're building AI for social good, the challenges, some of these challenges are familiar to anybody who does AI, but each challenge comes with its own flavor, so to speak, in the social sector. So I've listed 7 challenges over the next 2 slides. The first challenge is the data challenge. So you can expect almost by default that data that you have when you try to build machine learning models is noisy, it's incomplete, it's sometimes stale, meaning it's ancient data, it's not recent data, and it almost always comes in with non-uniform velocity. You don't have a fire hose of data that you typically have in an internet company setting. The annotations and labels are also often noisy, and you can hire expert labelers to decrease the noise, but then you compromise on scale. So this is, roughly speaking, the data challenge. Then there's the problem definition challenge. Where do we use AI? Where will AI make the most impact? And the context does not always clarify the specific nature of the AI problem. There's details like, is this going to be, is a classification problem the appropriate problem to solve? Is it a regression problem? Is it something else? And what specific problem, when solved, will actually make the difference that you intend to see? That's the problem definition challenge. Then this is a common challenge. What metric do you use? The metrics challenge. So defining the right metrics or for the AI to optimize, and specifying the right values of these metrics that you will need to reach in order to claim that the solution has achieved a certain level of success. Then you have the next, if you think of this as sort of a time sequence of events, the next issue you have is typically adoption, the adoption challenge. So there's cost to adopting AI solutions. They tend to be, especially recent deep learning models, tend to be rather large models. They have a large memory footprint and so on. There's a cost incurred by partners, and the cost is not just money. The cost could be time because they have to change certain workflows. It could be labor, it could be effort incurred by the partners in order to adopt the solution. And then there is a willingness, there's a suspicion of adopting solutions that are black box algorithms that are not, by their very nature, that are not perfectly explainable. Right? So that's the adoption challenge. And then there's a technical deployment challenge. Where will you adopt the solution? Is it going to be on device? Is it going to be on cloud? What tech stack do you integrate the solution with? Once you deploy, there's the evaluation challenge. How are you going to evaluate a solution that's deployed in a farm somewhere or in a village somewhere as part of a healthcare workflow? How do you enable the continuous evaluation that's necessary in order to make sure your AI is still working, right? And as many of you may know, those of you who are working in the space, it's necessary to continuously evaluate AI models. How do you design the right A/B test when the output of the AI solution is actually going to change outcomes, and you want to assess impact? You will have to design A/B tests, and that's a huge challenge. And then finally, there's the iteration challenge. Uh, AI is not like a standard software product. Usually, versioning is much more frequent because you need to retrain models as fresh data comes in. So you need an understanding and buy-in from the partners who are working with you to deploy your solution, that iteration is a necessary component of this. And you need to be able to sample and continuously annotate data as you go through the deployment cycle. So these are sort of some of the principal challenges in building AI in the spaces in which we work. And I'll go through specific examples of this. Sorry, 1 second. Yeah. So these are some of the areas in which we are currently working. We also have a number of other projects lined up. I'll describe these in some detail in the next few slides. But roughly speaking, the two domains in which we are currently working are agriculture and healthcare. In agriculture, we are building solutions for managing pests and therefore reducing crop losses. In healthcare, we have really two streams of work. One is in the area of maternal, newborn, and child health, where we are designing a sort of computer vision based solution that measures the weight of a baby. And this is something I'll describe in detail. And the other stream is in the TB and COVID spaces. The COVID space is something that we worked on in the past. We are no longer actively working on right now. So in pest management, really, we're working, most of our work is focused on cotton. Cotton is India's third largest crop. And in fact, pest infestations in cotton farms have led to a great number of farmer suicides in the past. In fact, cotton farming alone is responsible for the majority of farmer suicides in India. And this happens as a consequence of pest infestations. And so we are creating tech that will help increase both farmer income as well as yield by reducing crop losses. And the way we do this is through a computer vision solution where we take a picture of pests on a trap and we can estimate pest infestation on the farm and therefore recommend timely spraying of pesticides. We're also working on a more general solution that will look at other signals and will not need a trap. The next solution I won't say much about right now since I'm going to talk about this as a case study in a few minutes. Then we have a whole host of projects in the tuberculosis space. As some of you may know, TB is one of the biggest scourges in India. India carries about 1/4 of the world's TB burden and about a third of the world's TB deaths. And in 2019, we became the official AI partner for India's Central TB Division. India's Central TB Division, in fact, sits on the largest TB database in the world. So every patient who's diagnosed with TB across the country is tracked through that database, and it's called Nikshay. And so it's a real gold mine of data that you can use to potentially improve TB outcomes. And in current projects in this space, we have one project where, again, it's a computer vision project where we carry out automated reading of the TB line probe assay that's used to detect drug resistance to TB. And the other one is where we predict the risk of a TB patient not finishing their treatment in the 6-month treatment period. And we do this in advance just before they start treatment so that you can take interventions along the way so that patients, in fact, do complete their treatment. We worked with Mumbai city government as well as the government of Jharkhand to provide them with epidemiological forecasts for COVID cases. And this is a project that we did over the course of a year and a half. We've also developed an AI-based triaging tool that can detect COVID in cough sounds. So I want to talk briefly about the whole solution development process when we build AI. This is, in fact, a fairly standard process across all applied AI work. You start with a problem definition, you collect data, you label the data, you ingest the data in your modeling workflow, you carry out initial exploratory data analysis, the transformations that are necessary, do feature engineering, split your data, and then you apply a bunch of algorithms and so on, and then you evaluate your model. Then there is a passive deployment phase that is used to test your model, and this is important. This is somewhat separate from sort of evaluating your AI on internal data splits, but on completely unseen data, you need to mimic a real-life deployment, and that's what I mean by passive deployment. That's a sanity check that the model is working as you expect. And then there is a small active deployment or pilot phase where you actually deploy the model in the real world. And then you have to monitor and evaluate it, if necessary, iterate, and you go back. Right. So this is the standard cyclical process. The difficulties come in the areas that I've circled here. Right. Problem definitions are almost always very difficult. Data collection is a very lengthy process in the social sector. Labeling it, annotating it accurately is also can also be a time-consuming and laborious process. And then finally at the end, so it's really at the two ends of the spectrum that many of the challenges lie. Finally at the end, actually deploying the model, because that's where you have to, you encounter handshakes with various partners that you're collaborating with, and then monitoring and evaluating it. So as a case study, I want to talk about some ongoing work we are doing. This is not a model that's deployed yet, but it's one of the more sophisticated pieces of work that we are carrying out at the Institute. And this is our solution for newborn anthropometry. So I've mentioned various people who are working on the project here. This is the current team. It includes both machine learning scientists and engineers, program people, user interface designers, and so on. But there's also a number of people who worked on this project in the past who haven't acknowledged here. I would just run out of space. So the motivation for this problem is that there's about 20 million low birth weight babies born every year, and the infant mortality is about 4.1 million. Right? Now, the highest mortality risk is really in the neonatal period, which is the first 28 days of life. And interestingly, 60 to 80%, depending on location, of all infant mortality is correlated with low weight. It's both low weight at birth and low weight following birth in the neonatal period. So it's very important to be able to track the weight of the baby accurately, especially during the neonatal period, because if you can track accurately, you can carry out the right interventions, you can give the baby the right nutrition, you can do counseling to the mothers, and so on. So there are various issues with doing this measurement and tracking currently. So one issue is that the babies, at least in India, in rural India, aren't weighed accurately. The typical situation is that a frontline health worker or an ASHA worker goes out to villages with a weighing scale. And this is just a simple spring balance type of weighing scale. And these spring balances aren't calibrated accurately. So there's inaccurate weighing. On top of that, they are not read accurately. So there are human errors in actually interpreting the pointer on the spring balance. Then there's inaccurate, incomplete, and manual non-digitized reporting. And an example of that is what you see in the left picture here. So this is typical case sheet where every row is a baby. Typical case sheet where every row is a baby. I've blanked out the names for privacy reasons. And you can see the first column that's not blanked out is the weight of the baby. And you can see all of these babies seem to have a weight of 2.5 kg, if you can eyeball the numbers there. And this is clearly inaccurate. And this is typically written down because 2.5 kg is the threshold at which a baby is considered low weight. And if the baby is less than 2.5 kg, there are certain interventions that have to be done. And this is a way of circumventing those interventions. And really, there is nobody to blame because it is a very difficult job to go out in the villages and do this day by day. So it's a very taxing job for the frontline workers. And therefore, they tend to report inaccurately. And as a result of this inaccurate reporting, the babies get inadequate care and interventions. So our aim is really to accurately identify underweight babies and monitor their growth during the neonatal phase using an AI-based weight estimation model. And we call this a virtual weighing machine. And the idea is quite straightforward. It's sort of a touch-free system where a baby is put on a piece of cloth on the ground, and a frontline worker takes a short video of the baby using a smartphone, and that covers roughly a 60-degree range of angles. And using the frames in the video, we built a model that infers the weight. And this requires no weighing scale. This is obviously touch-free. Nobody needs to carry the baby. The entire workflow is digitized in the backend because the weight can be logged automatically and therefore should result in better monitoring. So this is the vision for the solution. We are not there yet in terms of accuracy, but I'll describe a bit where we are. There's sort of two possible ways to think of this problem. One is, this is from the technical perspective. One is as a classification task where you can think of it as a two-class problem, a binary classification problem, where you simply try to predict if the baby or estimate if the baby is low birth weight or not. I shouldn't say low birth weight, I should simply say low weight because this is after birth. And that's the problem we initially addressed because we simply didn't have enough data. And that was largely a consequence of the pandemic. The way we did the classification actually was by estimating the weight and then applying a threshold. But the more important problem, the one that will result in scaled impact in our view, is only possible when you estimate the actual weight of the baby. Because if you estimate the actual weight, then the neonatal care program is then able to track weight over time. It can address departures from normal weight trajectories. And then you can take nuanced decisions on interventions on the basis of how low or how high the weight is. You actually have sort of a continuous distance to some decision boundary. The risks of doing this, and one of the principal risks we found on the field is that doing this in a way that is agnostic to how high the smartphone is above the baby will require a reference object of fixed dimensions placed in the video scene. So basically you need some object that is always of the same size, no matter where you're doing this. And this object is used so that the model can latently estimate the depth meaning the distance from the phone to the baby, and hence can get an overall view of the scale or the size of the baby. Otherwise, if you don't have a reference object, the tendency is that if you go close to the baby, the model may actually think this is a big baby and therefore overestimate the weight. Conversely, if you go very far away, the model may tend to underestimate the weight. And so this reference object seems like something that is essential. Currently, what we are using for a reference object is a checkerboard, which is standard in computer vision problems that has fixed length and width. But this is something that we learned may not scale well in the field. It may not be feasible for the ASHA worker to carry this everywhere or for all ASHA workers to carry this. So we are also experimenting with other objects that these frontline workers routinely carry, like tapes that are used to measure the arm circumference of the baby, which they carry anyway, and simple wooden or plastic rulers. These experiments are currently going on. There's a technology challenge because the solution for training the model involves fairly substantial data collection. And then there's the internet connectivity issue, which we're still working through. If we host the model on the cloud, then the phone needs to be connected to internet. Otherwise, we need to compress the model to an extent that it can fit on a regular low-end smartphone without compromising accuracy. Then there are deployment challenges actually using this, because it requires a change in the workflow of frontline workers. It requires adoption of mobile phones in the ASHA worker program. This is gradually being rolled out across the country, but we are not there yet. And of course, requires buy-in from various state governments. So we are working through all these challenges. In terms of actual modeling, we initially started with what's called a model-based approach, which is really, when I say model-based, I don't mean a machine learning model. I mean really a model of the surface of the baby. And it's sort of a parametric 3D model. So we initially started by estimating a parametric 3D model of the baby, and then computing the volume enclosed inside this 3D surface, and therefore estimating the weight. It turned out that that was a very complex way to approach this problem, and very, very data hungry, and in fact didn't give us too much of a lift over a simpler method. And again, this is sort of temporary. If when we collect more data, it might give us a bigger lift. So we haven't shelved this approach yet. But the approach we are currently using is the so-called model-free approach, where you don't estimate a shape of the baby's surface, but rather directly estimate the weight of the baby. So there's an input video, and video is then chopped into frames. There's a CNN that processes one frame at a time, and producing an array of sort of feature representations for each frame, fixed dimension representations. And then these have to be fused in some way to solve a regression problem where you estimate the weight. And there are various ways of doing this fusing or pooling, which I'll talk about. So we started with a simple baseline where you treat each frame independently. So you don't do this pooling, but for each frame you predict a weight, and then you average or take the median actually across all frames. So if you just apply this very simple baseline, then and you look at, and we looked at two different settings. One setting is where the baby is in a hospital environment as a simpler problem. In a hospital environment, the baby is typically placed on a white sheet. There's uniform lighting and so on. And of course, our model did, even the baseline model actually did very well in a hospital environment. We got a mean absolute error in the weight of the baby of roughly 82 grams, which is in fact very good. But the same type of modeling, when applied in the home setting, resulted in a huge error of about 400 grams, which is a relatively large error. It's not, I wouldn't say it's huge, but it's still relatively large. It's certainly not acceptable for deployment in practice. So there's this big performance gap between hospital and home settings. There are various reasons for this. One is that the hospital doesn't have the visual diversity that you see in rural homes in India. The rural homes tend to be very, very diverse. The other reason is we had much less data from the home setting than in the hospital setting. We've tried methods where models can learn to generalize from hospital to home, but they don't, I mean, it's a fairly non-trivial task. So if you do a simple pre-training on hospital and then take that pre-trained model and fine-tune on data that you obtain from a home setting, it doesn't work well. It's just that the data is very different. So in a hospital setting, you have a plain background. In a home setting, you have varying illumination. The location of the checkerboard that you put in the scene seems to be important. The baby ages have greater diversity in a home setting. In home setting, we saw babies ranging from 1 to 42 days old, whereas in a hospital setting, typically babies in hospital, you only keep a baby in a hospital for the first 7 days. So there are many issues like this. So one of the approaches we tried was a transfer learning approach where we created what's called real data. And what this means is that you, in software, you cut babies and checkerboards from the hospital data. So you create this sort of virtual or simulated data set where you cut babies from hospital settings and paste them on empty home background videos. So we've taken videos in home settings that don't have babies in them, just background videos, and we actually paste them in software, and therefore create a training datum in this way, right? And this is what we call real data, basically a real baby superposed on a real background. And then what we do is we generated roughly 9,000 such real videos by pasting hospital babies on 5 different home backgrounds. And we can make hundreds of thousands more. I mean, this is a scalable process, but you don't get much advantage by scaling this further. And then we use this data, not the hospital data as it is, but we used this real data to pre-train our model and then fine-tuned on actual home data, right? Now, when we do that, our error improves from about 400 grams to a little over 300 grams. So there's a fairly substantial performance improvement. The other thing that we tried was a video pooling method. So if you recall, in the baseline, we treat each frame independently, but you don't have to do that. So we have another sort of fusion layer where you do either do a max pool or a mean pool across the frame representations. And then that gives you sort of a, if B is your batch size and D is the feature dimensions, then you get a B times T representation after pooling. And we regress the final predicted weight value on that. And that also results in a lift. These are hospital numbers, these are not home numbers. In the hospital setting, you get a lift from roughly 82 gram error to 74.5 grams. There are other experiments, a number of other experiments that our group has tried, a number of other transfer learning experiments like, placing the checkerboard in different positions, removing backgrounds, feature distillation, and domain adaptation experiments, as well as other video pooling techniques. These result in small improvements, but we think, as our data collection scales up, the improvements will be better with some of these techniques. So these are our current results. In a hospital setting, the graph on the left really addresses a classification problem where you classify a baby as low birth weight or not. And the graph on the right shows you results for the regression problem where you're trying to estimate the weight. And on the classification problem, we can get both recall and precision at above 90% at a single operating point. Which is very good, but this is in a hospital setting. For the regression problem, we can get a mean absolute error of 74 grams with 90% of the babies having an error of less than 150 grams. So, at least in a hospital setting, this problem is essentially solved. In the home setting, things look different. So we're only showing you the results for the weight estimation problem in a home setting, where our current best mean absolute error is roughly 300 grams on the baby. There's various things you can do to improve this. So you can have a preprocessor that only says, we're going to use an operating range of 1.8 to 3.5 kgs, which covers roughly 88% of babies in a population. And then your mean absolute error reduces substantially. But this is something we're still working on. We've also worked on some visualizations of the feature representations that we get in the penultimate layer. So as you can see, this is just a t-SNE representation of the two main dimensions. And what you find is that the babies do cluster quite nicely. So the orange ones are normal birth weight babies, the blue ones are, the orange ones are low birth weight babies, the blue ones are normal birth weight babies, and you can see that they cluster separately. And in fact, even if you fine grain the clustering further, the clusters do separate. That you can see that in the right graph. Those are various weight ranges, as you can see in the legend. Purple is between 1 and 2 kg, red is between 3.5 and 5, and so on. So this tells us that the approach is promising. And furthermore, we also find that the val set is well distributed among the training set. The val set are crosses, the training set are the dots. And so we're quite optimistic that given enough data, we can improve this to a point where it's usable. So future plans really on this project are we're doing ongoing data collection in rural home settings in Punjab and Gujarat. And really our target for deployment is to get less than 150 grams error on more than 90% of the babies. We are looking at errors in the current workflow that the frontline workers use. We want to make sure that we're not too ambitious for the AI. We really need to understand what the errors, what the effective error is in the current workflow. The effective error being a combination of, reading the spring balance and then logging things accurately and so on. We are also working on ways to converge on the right reference object to use. We can't use a checkerboard, then how well does the algorithm work with a ruler in the scene or one of these MOAC tapes that measure that are used to measure arm circumference. On the technical side, in addition to what I've mentioned earlier, we're looking at multitask learning, sort of jointly estimating weight, length, head and chest circumferences. The model-based approach I already talked about, and we're also looking at learning baby shape representations through a self-supervised contrastive learning technique. We have a number of partners in this project who are helping us with data as well as field implementation, as well as we are funded by the Gates Foundation and the Botnar Foundation on this, in addition to in-house funding that we have from the Wadhwani brothers. So there are various lessons we learn from these types of projects. So this was just one example of a solution that we are working on. We have, as I mentioned, we have a number of solutions like this at various stages of maturity. And there's various lessons we've learned along the way. So one of them is annotation is absolutely critical, and the expert annotators have to be trained. So even domain experts may need additional training because they're not exposed to AI. Choosing the right metrics. Metrics should really capture your user requirements. This is a lesson known from the internet industry as well. And you may have to introduce two different sets of metrics to optimize in the short term for the AI and in the long term for the solution itself. You need models that are appropriately localized to your context, right? A model that works in Rajasthan may not work in Telangana. So you have to be sensitive to that. And finally, offline inference is often a huge issue. So just putting a model on a cloud somewhere and doing an API call is often not enough because of internet connectivity issues. And so you have to work on compression techniques, model pruning, etc. And then finally, you have to ensure that data privacy is retained through the whole process, and you have sort of low latency solutions. So with these kinds of problems, there are a number of research areas that we already see opening up. We are about a 3-year-old institute, and we're just sort of gaining traction in the recent months. And we're already seeing a number of areas that are amenable to applied research. In computer vision, areas like depth estimation from monocular images and video, segmenting moving objects, estimating the shapes of 3D objects, super resolution techniques, where if you take a picture with a very low-end mobile phone and you still need a high resolution picture, can you use machine learning? Can you use learned models to improve the resolution in software? There's NLP and speech related areas. Speech to text in vernacular languages is going to be useful across the solutions we work on. And in general, it's going to be a great help in digitizing data across India. Knowledge extraction from free-form text, again, across languages is going to be an important problem. When you have to pass, for example, medical notes, or you have to do media scanning of news articles and so on to catch epidemics, for example. There's other deep learning areas where areas like time-aware deep learning is useful. Deep learning for tabular data, traditionally deep learning has not been very successful with tabular data, but that's an open research area that we can directly use in many of our projects. And then general machine learning techniques. So for example, mixed classification regression problems, outlier detection, problems involving multiple labeling and noisy labeling, data imputation techniques, cost-sensitive loss functions, and rejection models, where you send some of the data to a human in the loop, and how do you optimize this relative ratio between human in the loop and machine in the loop, right? This is also an important area. And finally, reinforcement learning types of problems where you want to find certain individuals in a population through intelligent sampling. I'd like to end with this slide here. This is sort of general observations on how AI can be useful for social sector, for social good, and also how smartphones are sort of driving this. So on the left, and this is for from the McKinsey Global Institute. On the left, you see, sorry that it's not very clear. On the left, you see along the rows different sort of AI capabilities or techniques, and along the columns, sort of various UN sustainable goals, sustainability goals. And you can see the AI techniques pretty much span every sustainability goal. So given enough data, there's a lot of ways in which AI can impact society, and this is only increasing. And you can see this also from smartphone penetration. A lot of the AI that will be developed for the social sector will be used on smartphones. A lot of the data will be captured through smartphones. A lot of the inference will be done on smartphones. And you can see the estimates of smartphone penetration across the developing world in the right figure. So on the left, you have the 2017 estimates, and on the right you have the 2017 actuals, and on the right you have 2025 estimates. And you can see the anticipated increase in smartphone coverage. The smartphone here is in light blue. So in sub-Saharan Africa, for example, only 8% of sub-Saharan Africa was covered by smartphones in 2017, estimated to rise to 38%, and so on, right? So along with the technology developments in deep learning, along with their applications to various UN Sustainable Development Goals, there's also this increasing rise in smartphone penetration. And I think the synergy between these two is only going to drive work further in this field. And we are very excited to be sort of at this stage. So I'd like to end there. Thank you very much. I'm happy to take your questions.